Hello, everybody, and welcome back to the wonderful world of statistics. Um, we are going to be doing confidence intervals today, and we are going to be doing 4 types of confidence intervals. If you want to just make note of the types of confidence intervals we're going to do, we are going to do, come over here, Z intervals. Okay, we use Z intervals when sigma is known, right? Then we are going to do this little star here, T intervals, and that's when sigma is unknown. Okay. Then we're going to do proportion intervals. Which is going to be easy because they're not going to give us sigma or standard deviation or mean or anything. They're just going to give us sample size and how many were successful. Basically, it's binary. Yes or no, pass, fail, succeed or not succeed. So proportion intervals, we'll do those, and then we're going to do this really fun thing, which is chi-square intervals. So, yeah, we're going to look at all 4 of these. And again, take notes, but you know the drill. Most of this is going to be done on R for us. So don't take serious notes of the formulas unless you really want to, because I'm going to show you how to do this all on R. And what I want you to do is know what we're going to use this for. What is the point of creating intervals? We're going to talk about that. So not only do you need to know what the intervals mean, how to find the intervals, you really need to know what does the answer mean? What does the answer actually say? Okay, that's what we're going to get into today. I'm going to continue on. So, first section, constructing confidence intervals for a population mean when the population standard deviation is known. So Z intervals first. We're going to compute point estimates. Okay, we're going to construct and interpret confidence intervals. We're going to look at the role of margin of error. We may breeze through that. And then we're going to determine the sample size necessary. Now, this is not going to be done on R, so you're going to want to make sure you write down this formula because it's a really simple formula. I may be able to find this on R, but to be honest, it's not super necessary. Okay. We'll see. I'll see if I can find something on this on R. So, let's get started. Compute a point estimate for the population mean. Now, I would go through this, and I'm going to move on through the PowerPoint. But I'm just going to write this down. Your population mean, if you remember the symbols, top mean symbol is mu. All right. We are going to say the best point estimate. We are going to say, the book is going to tell you because it's true, point estimate. Basically, if I don't know what the population mean is, and it's often the case I don't know what the population mean is, what's the best estimation for it? That's the sample mean. If you remember the sample mean, that's X bar. Sample mean is the best point estimate. So you're going to see that this right here, they're going to use this. It's the same. That's what this is. Okay, that's the same thing. So this is equal to mu. That's the point estimate of the mean. I'm going to say that's approximately the mean or close enough, or a really good estimation is the mean of the sample. That's really it. Compute the point estimate basically means find sample mean, and you already know how to find sample mean on R, so I'm going to move on. Moving on. All right. Construct and interpret confidence intervals for population mean. Now, I'm going to write down what they are, and you're going to see this later on. Okay, it's just how PowerPoints can be very busy. So again, if you remember what interval means, okay, interval. If you remember, what were those called? Interval notation back in algebra 2, college algebra, pre-calculus. not statistics, but calculus. We did interval notation. I mean, those are in calculus right now. Know the bounds of a to b. This is the interval in which we are doing definite integration. So kind of same concept. We need two numbers. We need two numbers, a and b, that represent a boundary for which somewhere between a and b, the true mean, the true population mean, mu, exists. So we're going to basically create an interval in which we have some level of confidence, 90, 95, 99% confidence, that the true interval is in between those two numbers. Okay, so with that, we have a lower bound, which is a. So a is our lower bound. Which is x bar minus what they call z alpha over 2 times sigma divided by square root of n. And again, you don't have to remember this formula. Okay. Though we'll kind of put this on R, so it's not bad to write it down. Upper bound is x bar plus z alpha over 2 times sigma divided by square root of n. Now, I'm going to go ahead and you will just go ahead and write this down because it doesn't hurt having this information. I'm going to give you some confidence levels and corresponding z alphas. Okay, so we'll go confidence level and their corresponding z alpha over 2. This is called the critical values. All right, so we'll start with 80%, and that is 1.28. 85%, 1.44. 90%, 1.645. 95%, 1.98. 98%, 2.33. And 99%, 2.575. Okay. So if we do a confidence interval by hand, that's where we will find z alpha. Everything else we'd be given. We'd either be given the sample mean or we'd be expected to find the sample mean. We had to be given standard deviation because it says the whole point is this is known. And the sample size we're either given by a value, like they either tell us how big the sample is, or they give us the raw data and we can just look how many numbers do we have. So this is what we're going to do on R, okay, is run this formula. It's just there's a specific formula for z alpha over 2. So let's bring up R. Give me a second. Actually, let's go ahead and look at one of the questions that says find the confidence interval, and we'll do this formula real quick. So, hopefully you wrote all that down, or pause the video and rewind a little bit and paused it and wrote it all down. Right. Oh, wait, there was one thing. In order to do confidence intervals, we have to have one of two things. Either the question straight up tells you that the distribution is normal, okay, or approximately normal, right? Or we can assume it's approximately normal if it's a large enough sample size, and the sample size must be bigger than 30. So if your sample size is bigger than 30, you don't have to worry about anything. But if it's not bigger than 30, you have to see somewhere in the question that the distribution appears to be normal or seems to be normal, has some type of normal distribution. Okay, it needs to be written in the question somewhere. Otherwise, this really is kind of not a good estimate. Okay. So let's look at a question. So there's the formula. Okay, so here we have. No, let's not do that. Find one. Come on, here we go. Construct a 99% confidence interval about the population mean weight in grams of pennies minted after 1982. Assume that sigma is 0.2. Now I've gone ahead and created that file in Excel. Okay. So what I'm going to do is open R. Open RStudio. And I'm going to run this format. Now, the only thing I need is the sample mean. All right, I'm already given sigma. I already have the confidence interval, which means I would use, 2.575 for z alpha over 2. All right, so here, so here's, again, I didn't make note of this, but I really want to make note of it now. Make sure you set this up correctly because it's different now. All right, on the computers at school, there was nothing else hooked up to your computer, so anytime you hooked up a jump drive or USB drive, it was automatically D, and that was it. You just had to do D and then R data, and that was all you had to do. But on the computer you're using now, you may have to make sure where that is located. Is it D? Is it H? Is it G? Is it I? I mean, you have to make sure what the file location is, so make sure you get that correct. This is what is for me. This is where I put my files. So, I'm gonna run that real quick, just make sure it's good. This is the file for penny. Okay, I just made it penny. Here's make a note. Please make a note of this. We are going to stick to CSVs today, and I'm going to show you what I mean. I'm going to open up this file, PowerPoint, our data. There it is. Now, .csv doesn't really change anything on Excel. Kind of see, not really because it's tiny. Kind of see that it's the same. Okay, so what I'm going to do is when I save this, when you make your Excel file, because yeah, you're going to have to make your Excel files here. Should have some of the data kept up on your jump drive, but if you don't have your jump drive, yeah, you're gonna have to make your own Excel files. Okay. So when you do save your Excel files, so file, save as, make sure that you don't choose workbook like we've been doing. Okay, you want to use CSV, and you got to be careful because there's 4 different options. There's CSV UTF, which I don't know what that is. Okay, I don't. And then there's CSV Macintosh and CSV MDOS. I don't know what those are either. I am going to be using CSV, delimited. Okay, just CSV, delimited. No special, no UFT, delimited. Just CSV, delimited. And there's a good reason for it. And it's because last year I found out whenever I ran the formulas for confidence intervals, they didn't like you doing anything other than CSV files. If I could tell you why, I would. I don't know. Okay, so just make sure you save as a delimited. Save. Starting there, you want to replace? I don't really. I cancel because I don't want to replace. So, there it is. Make sure, and now when you put it in here, this is how you're gonna type it in here because it's different. It's not the read XLSS whatever it is anymore. It's read table penny.csv header equals true. Only put header equals true if you have a title for your column. So back here, there's a title here, so there's a header for this. So header equals true. That means that when you calculate things, you won't use the initial value. You won't use that first line because that's a text line. If you put header equals false, I'll show you what's going to happen. Because right here, this is my answer when I calculate mean. If I put header equals false, that means there is no header, and the first input is an actual value. Okay, so run that, and then run that. It's going to say argument logic, blah, blah, blah. So it doesn't like it. Now, if you don't have a header, if I took the header off, it would be fine. Okay, so I'll show you. I'm going to take that off. I don't need it. Delete. Okay, I don't need that anymore. It doesn't have a header. Okay, run, and now it's also not fine. Okay, Oh, I don't know if I saved it. Save. There we go. Now run it, and run it, and still not working. Okay. I'm just going to undo everything because it was working before, so I'm going to leave it as header equals true. Right, and then I'm going to leave that in here as here. Save. Run this now, and then $ pennies. Now I shouldn't have any option, shouldn't have any trouble. There we go. There's the sample mean. So I'm going to set up that formula, which uses X bar, right, and uses sigma and n, okay, and then our confidence level, CL confidence level. So this is the sample mean. You don't have to type any of this in, all right, but I'm just kind of putting notes on R, and I'll post these notes as well. This population standard deviation. All right, sample size and confidence level. So, and the formula uses X bar. And again, you have your lower bound and you have your upper bound, and the only difference is this is a plus, that's a minus. So X bar minus Q norm. This right here is going to find that Z alpha over 2 for us. So, yeah, so Q norm of parentheses, 2 parentheses, 1 plus CL divided by 2, close parentheses. So that's going to find that Z alpha over 2 for us. And then sigma divided by the square root of n. So we're going to use this as the mean. Okay, we had a 99% confidence level, so 0.99. Our standard deviation was 0.02, and we had a sample size of 17. We had 17 numbers. So plug all that in, and we get lower bound, say, I'm just going to do LB equals, instead of go to 2 decimals, 2.452. We'll go to 3. Why not? One more than the number they gave us for standard deviation. So upper bound, so UB equals 2.477. Right? And that's how we're going to do Z distributions. Find mean. If they didn't give us mean, we have to find mean. They're going to give us everything else. They may not give us sample size. Again, that's just how many numbers I have. So sample size is easy to find. They're going to give us confidence level, and they have to give us population standard deviation. Otherwise, we're not doing a Z distribution. We're doing what's called a T distribution. Okay. Save this. Back to PowerPoint. And there it is. Again, you're going to notice they're a bit off, and there's a reason why. It's because they round where we don't round. See how they rounded the sample mean, and we didn't round the sample mean? So again, they're a little off. All right, roll of margin error, constructing confidence interval. Basically, that second part, that Z alpha over 2 times sigma divided by square root, that's called the margin of error. And that's it. So this part right here has the margin of error. 0.0008, that's the margin of error. All right. So I'm not going to go any further in that. All right, now this form you're going to want to write down. So in what this formula does is let's say that I want to have a specific margin of error for my survey. Let's say I'm surveying what favorite pizza topping people has. I don't know what I'm surveying. Let's say survey if people actually like pineapple on their pizza or not. Yes or no, pineapple, yes or no. So we go out and we survey people, And I want my margin of error for the true population mean of how many people, or the average number of people who like pineapple on their pizza. Most time, this is kind of a ridiculous concept, so let's look at something a little more. Sorry. A little more down to earth. Let's say that we salary of teachers. Hey, remember that project we tried to do? So let's say we're looking at average salary. We can go out and collect data, and I wanted to find the true population. What is the true average? But I also didn't want to be off by that much. I wanted to be off by maybe a couple $100, maybe $100. I want my average to be within $100 of what I have, or even $1,000. Be more realistic, $1,000. So plus or minus $1,000. Well, in order to limit your margin of error, okay, we have to do one of two things. We could, one, change the confidence level. The higher the confidence level, the larger our margin of error is going to be. So if we want a smaller margin of error, we would lower our confidence level. So we're just less confident. And we'll talk about what that means, confidence means in a minute anyway. But another way, and the more practical way to do this, the more realistic, what actually is going to happen, is you would increase your sample size. Which again should make sense, because the more data you collect, the more accurate your survey or your interval is going to be. So this is a specific way. It says, well, if I want to have a specific margin of error, I need to know how many people I need to survey. So I want to know how many people I must have to have a margin of error no bigger than this number. And this is the formula for it. So I'd write down this formula, and that's when you're going to use that table that we made at the beginning, the confidence level and the Z alpha over 2 table. So this is where you would use it, because I'm not going to give questions on that. We'll go ahead and do this one. Let's say we have, back to pennies, how large sample would we require to estimate for our margin error to be within 0.5 or 0.005. So let's do this. We know that the confidence level is 99%, which means Z alpha over 2 from that chart we made is 2.575. Sigma is 0.02, and the margin of error they gave us to be 0.005. So using the formula, N is equal to Z alpha over 2 times sigma over E squared. That's going to be 2.575 times 0.202 over 0.005 squared. Right, so I'm going to put that calculator, and here's my calculator. So parentheses, fraction button, and that is 2.575 times 0.02 over 0.005, close parentheses, and squared, gives me this, which I need to change this out of signed notation. I was messing around with it. So mode, normal, I'm going to run that previous formula again, and we get 106.09. Now here's the rub on this one. Here's what you have to remember to do, and just make sure you take really good notes of this. We cannot have a sample size lower than this number, which means I cannot have a sample size of 106, because 106 is lower than this number. All right, this is my least amount of sample. Okay, that's my least. I cannot go lower than this. And so what I'm trying to say is you're always going to round up. Basically, you're always going to drop the decimal and add 1, because we can't survey 0.9 of a penny. Okay, but I can't have any lower than this, because if I even go 9/100 lower than a penny, if I take that off, that's going to be off by more than 0.005. The margin of error will be bigger than 0.005. Not by much, most likely, but still, it doesn't matter. The point is, always drop the decimal and add 1, so we should get 107 as my answer. So this, hey, 107 is the answer. 107 is the answer. Always drop the decimal and add 1 when you're finding sample size, so just make sure you take note of that. All right, so that's really it for the first section. So we're going to go into 9.2. Okay. Now, 9.2 is when we're using t-distributions. And again, I would love to go into student and the whole history behind this t-distribution, but it's late and I'm tired and I got more videos to make, so I'm not going to. I'm just going to go right on into this. T-distributions, if you remember Z, okay, you remember Z, write that out. Z is equal to x bar minus mu over sigma divided by the square root of n. It's the same thing, except for what? That. We don't know what sigma is. Okay, we don't know the population standard deviation. And that's the issue. We don't know what it is. So what's going to happen here is t is going to change depending on how big my sample size is. Okay, so there is no way, like, you know how I gave you a chart of z alpha over 2? There's a huge chart that I no way that I can memorize for t alpha over 2. There's no way I can memorize it. So I'm not going to. Instead, I'm going to just let R do the work for us. So don't stress this at all. I'm just going to let R do all the work. So, we're just going to keep going. Important, not really important t values. I'm not going to do. Here we go. Construct and interpret confidence intervals for population mean using t alpha over 2. Okay. So here's your information. Okay. And we want a t distribution of this. Right? So here's what we're going to do. What is this for? This is for pasteurized milk. So we're just going to go with milk. Let's make an Excel file. Excel, there we go. File new. So we'll call on, I said new, file blank. Doing. Oh, it's on my other screen. Okay. Yeah, I have a couple screens. All right, so we have sample, which we really don't need sample. What we're doing this for? We're doing for the CFU 8.96, 1.9, 1.4, 1.793, 0.49, 0.95, 15, 12. That's odd. That just up for no reason. And 0.38. Alright, I don't know what any of this means. Okay, we're just going to read all this. Pasteurized process reducing the amount of bacteria found in dairy products such as milk. The following data amounts of bacteria in pasteurized milk. And CFU, I don't know what CFU stands for. Per milliliter for random sample 12 pasteurized glasses. This is data concern, whatever. So that's my data. So I'm going to file save as. Put this in my R data file. Change this to CSV. Make sure CSV comma delimited. Okay. And just call this milk. Save. All right, we'll close it because I don't need any more. That. Close that. Let me R back up. Okay. So I'm going to do a t distribution, which is somewhere on here. Okay, now for t distribution, we're going to need this information. Okay, x bar, sample mean, sample standard deviation, sample size, degree of freedom. Now, degree of freedom is found by using the sample size -1, and then confidence level. So I'm going to have to upload information about milk. So let me insert, copy and paste this, because why would I redo the whole thing? And milk. Run that. And this is milk $, FU. Also need mean, so mean of milk $. Alright. So we have our mean and our standard deviation. We'll just go ahead and round these to 2 decimal places. So 6.41 and 4.55, because that's approximately close enough. So we have 6.41. So 6.41. 6.41. And then we use QT. QT instead of Q norm, because that was normal distribution. This is T distribution. How big was my sample? How many? There's 12. Okay. So our degree of freedom should be 1 less than 12. So degree of freedom should be 11. Okay. And they wanted a 95% confidence. So 95. And then our standard deviation was 4.55. So 0.55. 4.55 with the square root of 12. All right, we're going to run that. I think I deleted something I shouldn't have. Really, it's the same thing. So we have our lower bound and our upper bound. So our lower bound is 3.519. Our upper bound is 9.30. Okay. There we go. There you got 3.519, so 3.52 and 9.30. So yeah, we're good. That's how you do T distribution. This. I'm not going to mess with this. Moving on. So we've done Z distributions and T distributions. So let's look at P, our proportion, intervals for population proportion. Man. All right. Okay. Okay, I fixed it. Sorry, I did get rid of something. Before I had square root on there. I'm not supposed to square root it. Okay, so I'm taking the square root off. All right, so I'm taking the square root off. So if you paused it to write this whole thing down, just make sure you just take the square root off. So that's what it should be. It should just be v, the variance, times your degree of freedom. Okay. Over the chi-square of 1, for the lower bound, it's 1 minus your confidence level over 2, comma degree of freedom, and then lower tables false. For upper bound, it is the same thing, but 1 plus your confidence level. So that's how you tell the difference. And again, if you look over here, you're using, this will be 1 plus your confidence level. So it's going to give you your upper bound. Okay, this is for your upper bound. This is going to be 1 minus your confidence level over 2. That gives you your lower bound. So, degree of freedom, your variance, that's your numerator. So variance, degree of freedom, and then there's your denominator. If there's anything else, I think we're good. Okay, I think we're good on everything. That covers all your confidence intervals. Covers all your confidence intervals. All right. So, have questions? Feel free to email me. Now, I'm going to tell, again, Edmodo as well. I'm going to let you know that I'm going to be answering a lot of questions next week, okay, because my wife is due on Sunday. And so sometime next week we're expecting to have our child. And we'll let you know eventually. But next week I probably won't be doing a lot of work. I won't be responding to emails or text or questions. I'm sorry, Mira. I won't be responding to questions as quickly. Try to watch over the video again, see if there's anything wrong with this right here. Hopefully I'm going to give you straightforward questions that don't ask a lot of different weird things. So I'm not going to give you a lot of these to do because that's a big chapter, and there's 4 different things you got to do. Especially you have to do other stuff as well, not just stuff on R. When finding your sample size. So I'm not going to give a lot of homework on chapter 9, but I will give you enough to know what's expected on the final. All right. Have fun. Good luck. I hope you enjoy doing your homework and make sure you stay safe, stay healthy, wash your hands, all your fun stuff. Well, have a good night.